Good morning. Today our primary objective will be to determine the force acting on a toy train while slowing down to a stop. And so this is what the diagram looks like. We have a force that's opposing the motion, and the question is, how large is that force? We'll only be interested in the force acting while the train is actually slowing down or stopping. Secondary objective is to determine if the force changes when mass is added to the train. If we make the train heavier, does that have any effect on the force? And so to accomplish this secondary objective, we're going to have the train at three different weights. You can see the top weight there, 473.7 grams. Then we're going to add something to the train, 626.1 grams. And finally, we're going to add two objects to the train, 829.6 grams. Is the stopping force affected by the mass? And so the question is, how are we going to measure force? Well, we could use the formula F net equals ma. However, today we're going to use another concept. We're going to use the concept of net work equals the change in kinetic energy. So ultimately, in a few moments, what you're going to see is that general equation, net work equals the change in kinetic energy, can be rewritten as force times distance equals the initial kinetic energy. And so to see this derivation, the question is, what is net work? To answer that question, we'll start off with what is work? Work is a measure of energy transfer, gain or loss of energy, when a force acts on an object over a distance or displacement. The definition of work is force times distance times cosine theta. Now this definition assumes that the force acting is constant. So throughout our investigation today, we will assume that the force that's slowing down the train is constant. And so what is net work? Net work is the sum of the individual work done by each force. So if there's two forces, we see a sum of two different work values. If there's a third force, then that equation would be adjusted to write plus W force 3. Well, today in our investigation, we'll assume that while the train is slowing down, there's only one force acting. We'll also assume that that one force is constant. And so, continuing on with our derivation, net work equals the change in kinetic energy. Since there's only one force acting, we only have to be concerned with one work value, the work done by the force acting while the train is slowing down. So the equation, once again, given for work is force times distance times cosine theta. This is the definition of the force. It's opposing the motion. And this is the distance, d. D is the distance from when the train begins to slow down to when it comes to a complete stop. So what is theta? Theta for this situation is 180 degrees. Why 180 degrees? Well, if the two vectors, the force and displacement, are pointing in the same direction, theta is 0 degrees. When the force vector is perpendicular to the displacement vector, theta is 90 degrees. And finally, in this situation, as you can see, the force vector is in one direction, the displacement vector is in the opposite direction. When they're in opposite directions, theta is 180 degrees. And so in this situation, you can see force and displacement vector are in opposite directions. And so substituting, we know that cosine of 180 is -1. Now we're going to simplify. And there's our equation. And so the question is, what is delta EK? Well, any change in a value in science is the difference between the final state and the initial state. In this case, the change in kinetic energy is the difference between the final kinetic energy and the initial kinetic energy. Well, we know that the final kinetic energy is zero. This is because we know the train comes to a complete stop. The final speed is zero. Therefore, we have this statement here. Remember that kinetic energy is half mv squared, where m is the mass and v is the speed. And so we end up with this. And further simplifying, we end up with this final equation. Force times distance equals half mass times speed squared. So to measure force, we need these three quantities: distance, initial speed, and mass. So to determine the distance and the initial speed, we are going to use the motion sensor that is circled in the diagram there. How this motion sensor works is that it emits sound. You can see the sound represented by the white arrow. The sound is going to encounter a surface, the flat surface that I've put at the front of the train. When sound encounters that flat surface, it's going to reflect. It's going to reflect in the same direction from where it came from. Reflected sound is detected by the sensor, so the same sensor that creates the sound also can detect sound. The computer of the sensor can determine the time it takes for the sound to travel from when it left the sensor to when it came back. The computer also knows the speed of sound, so those two variables, the time it takes for the wave to travel back and forth and the speed of sound, the computer can determine the distance between the front of the train and the sensor. It can also determine the speed of the train. In real time, the sensor, via Bluetooth, sends data on time, speed, and distance to an app. This app is usually on some sort of mobile device or a tablet. And so this is a screenshot of the information that is displayed in an app. As you can see, velocity on the left side and position on the right side. For all trials, a screen record of the data is captured mainly while the train is slowing down. And so we have an acceleration phase here. And during the acceleration phase, there is no motion information. This is because the sensor there, which is circled in white, emits sound in that direction, and it has nothing to reflect off of. For the sensor to work, sound has to reflect back to the sensor. And so right around at this position, once again the sensor is circled in white, at around that position the sensor will begin to detect the presence of the train and can measure its speed and position. Today I'd like you to copy down the following table, and this is what you'll be submitting to me eventually. Alright, for the first 5 trials, the mass of the train is shown there. Here we go. So this is what the trial looks like. I did that 5 different times. Here's what the data looks like. It's very quick because the train stops relatively quickly. So from the video you just saw of the screen capture of the data, I have extracted 2 still images. The first image, where it says initial speed, is the speed of the train just before I turn the train off. So the speed of the train before I turned the train off was 0.41 meters per second. The position, the exact position at which I turned the train off, happened to be 1.03 meters. Once I've turned the train off, it then coasts to a stop. It came to a complete stop at a final position of 1.12 meters. And so with the initial position of 1.03 meters, this is the position of the train as I turned it off. And the final position of 1.12 meters we're going to take the difference of those two positions, and that will be our distance. And so there's our distance for trial A. Our speed is circled. That's the initial speed. That's the top speed the train achieved just before I turned it off. So in this situation, for trial A, our speed is 0.41 meters per second. And so here's our formula. Force times distance equals half mass times speed squared. The mass is listed there. So please substitute your numbers into this equation to get the force. Remember, if you leave the mass in grams, force will be the unit of millinewtons. So if you want your force in newtons, you need to convert your mass into kilograms. Once again, if you want your force in newtons, you need to convert your mass into kilograms. Please be aware of that. All right, here's trial B. And here's the data for trial B. Trial C. Here's the data for trial C. Trial D. Here's the data for trial D. And trial E. Here's the data for trial E. Next, we add this small little plane on top of the train to increase its mass. So this is the mass for the next 5 trials: F, G, H, I, and J. And there's our train with now the added mass. And here's one sample run. All right, here's the screen capture data for all the trials together. Here's trial F, G, H, I, and J. In addition to the data being displayed on the app, you can export the data to an Excel file, and that's what I've done here. So I've on purpose chosen the specific data where the top speed happened. So at 6.9 seconds, that's when we had the top speed of the train for trial F. And you can see it there, it's 0.47 meters per second. At 6.9 seconds, I turned off the train. And then it coasted. It coasted until it came to a complete stop at 7.6 seconds. And you can see at 7.6 seconds, the speed is 0. Here's the data for G, H, I, and J. Finally, we have trials K, L, M, N, and O, and I have 2 ships attached to the train to increase the mass by an even greater amount. Here is the data for K, L, M, N, and O. Once again, just like the previous 5 trials, I've exported the data from the sensor into an Excel file. At 10.7 seconds, that was the point at which I shut off the train. And at that point, it had a speed of 0.37 meters per second, and its position was 1.33 meters. And by 11.3 seconds, the train came to a stop, traveling about 11 centimeters in total. The data for L, M, N, and O. Now, while slowing down, we made this assumption. We assumed the force acting was constant. Is this assumption valid? Does the data support this assumption? So let's see. Let's look at our data. This is one of the reasons why for 10 of the trials, I gave you the data in greater detail. If the force is constant, then the acceleration should be constant, given that the mass does not change. So is the acceleration constant? Does the data support this? Well, if the acceleration is constant, then the change in speed should be constant. So now the question is the change in speed constant while the train is slowing down? In this situation, from 6.5 to 7.5 seconds. Well, the answer is no. As you can see, from 6.5 to 6.6 seconds, the train speed has decreased by 0.07 meters per second. And once again, during the next time interval, from 6.6 to 6.7 seconds, it again drops by 0.07 meters per second, the speed of the train. So far, so good. It looks like it's constant acceleration. However, notice, during the next time interval, from 6.7 to 6.8 seconds, the drop in speed is 0.08 meters per second. And then it only decreases its speed by 0.05 meters per second. And during the next time interval, the decrease in speed is 0.10 meters per second. And these are all the decreases in speed during the time intervals of 1/10 of a second while the train is slowing down. So for the most part, it seems steady at 0.07 meters per second. However, there are certain times where that decrease changes. And so the acceleration is fairly constant, but it's not absolutely constant. Therefore, the force that was calculated during this experiment is at best an approximation, as the force is not constant since the acceleration is not constant. Now, if you have this train set, you'll know that the front of the train looks like this. Notice it has some curves. And yet, as you can see, I replaced the front of the train with this flat surface. And so the question is, why the flat surface? We have the flat surface to ensure the sound reflects back to the sensor. Without the reflected sound, the distance and the speed cannot be measured. And so with a curved surface, you may have a situation where the incoming sound hits the curved surface, but then it reflects at an odd angle, and it does not reflect back to the sensor. If this situation happened, then the sensor's data would basically return values that don't make any sense. And so I've been working with this sensor long enough to know that to avoid this complication, I just made a flat surface. And for the most part, in fact, for every data point I saw, all the data points made sense, meaning that the sound was reflecting properly off of the front surface. So I hope you enjoyed today's activity. I hope it gave you some insight into another way of determining forces, but also some insight into the force acting on this train.